Here we go. So we're in chapter 2 today. We've finished up with stuff that's going to be on the exam. We're going to talk today about conformations of molecules and mostly steric factors, which are all related to the fact that portions of molecules are surrounded by electron density, and that electron density repels the electron density in other portions of the molecule. And so there are this has an effect on the shapes that molecules adopt. I don't know that we'll talk too much about these first two examples because you will have seen them in your undergraduate course, and you will have had a chance, hopefully by now, to spend some time in Gaussian messing around with some of these conformations. A couple of terms that may be useful to you, I think, like I said, maybe most of you know this by now. When we talk about conformations, a very important thing is a dihedral angle. This has a technical definition. A dihedral angle is the angle between two vectors. You can also define it as the angle between two planes, but by a vector I mean you put a point here and a point there and then draw a line through it, and then you do the same thing there. And mathematically, if you've got those coordinates, you can determine the angle. And this describes rotation around a carbon-carbon bond. There is a sign convention for which way is positive and which way is negative, because the angle between two vectors is related to the dot product, which is related to cosine theta. So there is a direction to it. I have never memorized that. Convention, and I don't expect you to. In fact, what we do, as you've seen in Gaussian, is if we want to know a dihedral angle, we simply click on the four atoms and it tells us what it is. So nobody measures these things by hand anymore. All right. And of course, the dihedral angle, in order for it to make sense, you have to specify which two bonds you're talking about. So presumably, they've said, okay, we're going to think about this hydrogen and that hydrogen and what's the angle between them. And notice that at angles 60, 180, and 300, we're at minima, and that corresponds to staggered conformations, whereas if we're at 0, 120, or 240, we're at maxima. And your text shows, and probably in your calculations, what you did was calculate the energy of an eclipse conformation. To do this, you had to tell it to optimize to a transition state. We'll talk more about that later. That's actually an interesting computational problem, because for something to be a transition state, it's got to be almost exactly like a minimum force. If you move any of the atoms, there has to, let's see. A transition state is referred to as a stationary point. That means if you move in any of the atoms in any direction, it wants to go back to what it was, except for the direction that corresponds to the reaction. So in this case, that's rotation around the carbon-carbon bond. Here's butane. What do we need to say about that? You've got two different staggered conformations and two different eclipse conformations. Having methyl groups eclipsed is worse than having methyl eclipsed with a hydrogen. And gauche methyl groups, where the dihedral angle is 60 degrees, is worse than having the methyl groups anti to each other. Okay, anything we need to review there? I know I haven't gone through that in a lot of detail. No care, okay, sort of boring. Couple other terms that you may encounter just for sort of dihedral angles. Basically, there's a 50-50 line. If you're on this side of it, you can call the groups syn to each other, and if you're on this side, you can call them anti. If you're sort of within plus or minus 30 degrees of vertical, you can call that periplanar. That means occupying sort of the same plane. This is why you'll hear, if you're teaching 351 this semester, about how the E2 reaction involves anti-periplanar arrangement of beta proton with its leaving group, and that's the combination of those two terms. I honestly don't really bother with what clinol means, and apparently this is the convention sign. So clockwise is negative and counterclockwise is positive, I guess, for dihedral angles. Okay. And your book will give you some useful increments. It's good to know that each eclipsed carbon-hydrogen interaction is worth about a kcal per mole. And yeah, I think having alkyl groups gauche to each other is also worth about a kcal per mole. One thing your text points out is that gauche is not always bad. So there's this weird molecule, and physical organic chemistry can sometimes devolve into let's make weird molecules as weird as possible and see what their properties are. So this is an example of that. It's 2,3-dimethylbutane or something like that. And it turns out that having the methyl groups you might expect that this would be the best conformation, because at least, though you do have methyl gauche to methyl, at least you have methyl anti to methyl as well. However, what they found is the presence of these two methyl groups on the same carbon, they will tend to distort their bonding so as to be far apart, and when they do that, that causes them to get closer, at least in terms of dihedral angle, to the other methyl groups. This is sort of gee whiz, because I can't think of anything I'd ask you about this other than, oh, look at that. It's kind of weird. But your text says that if you arrange it this way, even though they're all gauche to each other, when they distort their bonding in order to get away from each other, they can do so in ways that don't smash into each other. It can get more complicated, and you've seen this maybe in your computational assignment with pentane. And I totally didn't understand this until actually I sat down and did the assignment myself. So there are just a couple of unique conformations in pentane. They're showing 3 here. There's actually one more that they're not showing you. But for the sake of our discussion, we'll call this 1, 2, 3, 4, and 5. And the two bonds that we're worried about are the bond between 2 and 3, and then the bond between 3 and 4. Now, as we've drawn this, if you were to put your eye in the plane of the page, and I'm a nerd, I can't resist every time I do this. It stopped being funny, but I still do it anyway. We have sort of bloodshot, evil Sith eyes looking down that carbon-carbon bond. You would see that you've got an anti-conformation. Another way to describe that anti-conformation is to say that that dihedral angle is 180 degrees. Another way people will describe this conformation is to give it the letter T, under a lowercase t for trans or anti. We don't typically use trans in a stereochemical sense that way, but you will, when people talk about conformations, you will sometimes see that notation. So we have trans or a 180 dihedral angle here, and then if you were to similarly take your evil Sith eyes and move them to look down the bond between carbon 3 and 4, you would also see a 180 degree bond angle, right? And so you could describe this conformation with 2 dihedral angles. You could call this 180, 180. You could also call this TT, or you could call it the extended conformation or the all anti conformation. But it's those 2 dihedral angles that define what the molecule looks like, or its overall shape.
So TT is just trans strands?
Yeah. One that isn't shown for you here is gauche trans or trans gauche, they'd be equivalent. That would involve rotating around this bond so that this methyl group was gauche to this group, which they're not showing that for you there. Let's look at this other conformation, and this one's kind of difficult because 1 and 2 are in front and behind each other respectively. We want to look down the bond between 2 and 3. I guess this wasn't ever a methyl group, was it? It was like some R group. We want to look down the bond between 2 and 3, and then the bond between 3 and 4. So if we looked down the bond between 2 and 3, let's see, we would have a hydrogen here, another hydrogen there. It looks like on carbon 1 is a methyl group, so let's put that there. Carbon 3 in the back looks like we have hydrogen, hydrogen, and then the bond between 3 and 4. So that first bond between 2 and 3 has a dihedral angle of 60 degrees. I'm not sure if it's 60 or minus 60. And that won't matter for the most part until we get to the conformation at the bottom. And then let's look down the bond between 3 and 4.
You would just call that last one Gauche, right?
Yes, this first one conformation is yeah, gauche. There is a gauche plus and a gauche minus depending on whether you rotate counterclockwise versus clockwise. And we'll look at these two last conformations because they both involve gaucheness, but one of them is different from the other. If we look down the bond between 2 and 3, you know what? Let's not draw this. Let's actually use a program where we can see the model. Is that okay? Maybe you can draw it later. I forgot. So Spartan lets you draw pentane, and then kind of fun, it has conformations. So there is the all trans conformation. We'll call this carbon here, well, we'll call this one 2, 3, and 4. Doesn't matter, we could have gone the other way, it's symmetric. Looking down the bond between 2 and 3, you can see that's a anti or trans conformation. Looking down the bond between 3 and 4, that's also an anti or trans conformation. That's the lowest energy one. We go up to the next one, and I'm going to cheat and forget which one was 1, 2, 3, and 4. Down the bond between 2 and 3. Oops, no. We've rotated that methyl group from being here to here. Sum that up. So that's gauche. And in the back, we're still anti. So that's an example of a GT or TG conformation. One is anti and the other is gauche. One is trans and the other is gauche. This is an example of a gauche conformation. So we're again going to look down the bond between 2 and 3. And let's go ahead and define the sign convention this way. Let's start from if the alkyl group on the front and the alkyl group on the back were eclipsed with each other. Let's say if we have to rotate the group in the front counterclockwise, that's plus. Okay? So this is a gauche plus conformation. Now let's look at, and we're looking at atoms 1, 2, and then in the back is 3, and then this is 4. I'm going to rotate this up so we can look down the bond between 3 and 4. And notice again, if we imagine starting out eclipsed, in which direction would we rotate in order to get to the carbon in the front to get to that Gauche conformation? That's also counterclockwise. So that's also Gauche positive. Now, so we would call this conformation Gauche plus Gauche plus. Whoa. Went to sleep. That's not good. And if we want, at this point, we can draw down the bond between 3 and 4. And again, you see that to get if we draw sort of a line from the carbon group in the front to the carbon group in the back, in both cases, the sense of that is counterclockwise. And so these are Gauche plus, Gauche plus. There's an equivalent Gauche minus, but the effect of that, if you look at the molecule, is to sort of keep those methyl groups on the end apart from each other. One's going this way, the other's going that way. You see that? So this is kind of hard to see, and so tell me if you don't see it, and we'll talk about it. Like, what's confusing so far?
I'm just, I guess, confused about the signs. Like.
Okay. So that's the sign of the dihedral angle will honestly depend on which carbon we're calling carbon 1 and which one we're calling carbon 5.
So the reason it's plus plus though is, can you just explain that one more time? Like how we know on this that plus.
Yeah, maybe instead of saying plus plus, we can say, is it Gauche in the same sense or in opposite senses? Is one right-handed Gauche versus left-handed Gauche? Because if you look down if you look down a carbon-carbon bond, there's two positions that are Gauche, right? One on the left and the other on the right. And if methyl group was here, maybe it's 60, and if methyl group is here, maybe it's minus 60. All right, so I'm not totally sure what the sign convention is, and we can pretend like we know it or pretend that we don't know it. Let's ask ourselves, is the group in the front on the left or on the right of the group in the back? It's on the left. So let's just call that plus. Okay, so that's a Gauche plus. If we look down the next bond, we can ask again, is the carbon in the front on the left or the right of the carbon in the back? It's left. So we got two left-handed Gauches. And the effect of that is to keep the methyl groups on opposite sides. Now, a question you could ask is, what would happen if you changed one of those from left-handed to right-handed? So your two Gauche conformations were now opposite in sense. Let's look at that. We're going to look, here's carbon 1, here's carbon 2. All right, the group in the front is on the left-hand side of the group in the back, so we'll call that plus. That's a left-handed Gauche, or a plus Gauche. Let's look down the bond between 3 and 4. The carbon in the front is now to the right of carbon in the back, so that's an opposite Gauche sense. And if you look closely, you can actually see that's a little bit distorted from a Gauche. The dihedral angle isn't exactly 60 degrees. And the reason for that is that when you have opposite-handedness Gauche, you end up having the two methyl groups directly sort of smashing into each other. And I think we can look at this in space filling form. You can see that's kind of a problem. Sometimes people call this a syn-pentane interaction, but that's what we've got pictured here. And this is an example of the gauche plus, gauche minus conformation. And I guess we can draw those Newman projections so that your notes will be complete. It looks like down the bond between. Sorry. Looks like we've got carbon 2 here, and then in the back you have the R group. And methyl group in the front is on the left side, so I guess we're calling that gauche plus. And then looking down the bond between 3 and 4, you would have this, and then it looks like a methyl group in the back. Now the alkyl group in the front is on the right-hand side, so this is gauche minus. So it's almost like these two conformations are diastereomers of each other. It's almost like you had a molecule that was RR and another that's RS. They're different. They have different properties. You can think of conformations in that way as well. And this is why, by the way, you could ask, why didn't we do the gauche minus conformation? The answer is it looks exactly like this, just opposite-handedness. It's the enantiomer of that conformation. Same chemical physical properties has to be, right? And why didn't we do the gauche minus gauche plus conformation? Same thing. It's the enantiomer of this conformation. So the idea is that when you go beyond butane and you start to have more methyl groups there, you need to think of not only short-range interactions, but also long-range interactions. If we considered each of these bonds individually, we probably wouldn't have detected that caused the methyl groups to smash into each other, right? But in fact, it did. And so as your molecule gets more complicated, you have to start thinking about these other issues. And this is a common enough issue that your text felt like it was useful to call out. Now, this actually gives us a chance to talk a little bit about a concept called preorganization, because if you look at that gauche plus gauche minus conformation, notice those methyl groups, carbon 1 and 5, are on the same side of the molecule as each other. And so a question you could ask is, well, why don't I just bond them together, right? 1, 2, 3, 4, 5. And so if you take those two and you bond them together, you now have cyclopentane, and you relieve that interaction by just enforcing it. There's angle strain and ring strain present in cyclopentane. But now you could have a gauche plus here and a gauche minus there, and it doesn't matter because these two are connected to each other. And the idea is sometimes in chemistry we can enforce an unfavorable conformation with a cyclic constraint. You use chemistry to pay the energetic cost of having things in a conformation that wouldn't normally happen. All right. Anything else you want to ask about that? Another kind of strain that's sort of related involves what happens when you put groups adjacent to double bonds. So let's just imagine a pi bond here, carbon 1, 2, 3, and then let's suppose carbon 3 has something on it, something that's not hydrogen. Oops. you might imagine that that could have steric consequences as the vinyl proton from carbon-1 smashes into protons from the sp3 hybridized carbon that was attached to carbon-3. And of course, I've drawn this in probably not the most stable conformation, because you could rotate around carbons 2 and 3 and bring this alkyl group over here. But the point is that if you have a double bond, there is a chance for steric clash between the substituents on carbon-3 and the proton that's on carbon-1. And this is called allylic strain. Sometimes it's called A13 strain. And this is something that is easy to forget about. And it's an easy question for like an OChem professor to ask you in your annual review or your proposal defense. Or, oh, well, you've drawn this, and what kind of strain, have you thought about what kind of strain is that's there? And then you will feel like, oh, I knew that at some point and I forgot it, and then they'll remind you. So just be aware of that and prepared for it. It actually has an important role in some research problems that people are working on in the department. So Professor Castle's lab published a paper in Orglet a couple years ago in which, let's see, this was like 2017, I forget. If you want to go look it up, you can just Google it. But Professor Castle's lab is interested in a class of amino acids that are called dihydroamino acids. And the reason they're called that is because they have a double bond between the alpha carbon of the amino acid and the beta carbon. And in particular, Professor Castle's group is interested in bulky dihydroamino acids. And they're interested in them because they believe they can restrict the conformational freedom of nearby let's see. Maybe that's not what I want to say. These dihydroamino acids are predisposed to certain conformations. If you notice in this amino acid, there are a couple of bonds that chemists are interested in for details of peptide and protein structure. There's this bond between the nitrogen and the alpha carbon, and then a bond between the alpha carbon and the carbonyl carbon. Those dihedral angles at those bonds are influenced by the presence of these bulky groups here. And this is an example of allylic strain, A13 strain, because the group on carbon-1 is bumping into, let's see, no, I got that. Sorry about that. I think in terms of, we haven't talked about this, but the nitrogen is maybe conjugated to the double bond, and so this is maybe the first position of our allyl group. So the substituent on carbon-3 can smash into the groups on carbon-1, like the proton or like this other group. And that steric clash between those two groups restricts the freedom that these amino acids have. I didn't really explain that very well.
Okay. Sorry. Why is it called 1,3? Because the interaction is between four.
Yeah. Why is it called 1,3? Because if you really look, the interactions between a group on 1 and a group on 4.
Yeah.
I don't know. That's always tripped me up. Because some jerk in the past called it that, and we've all stuck with it. So I think it has to do with the perspective that if you're thinking about building a molecule and you start here and you think, oh, I want to put something there on carbon-3, oh, that could then be a steric clash with something that was on carbon-1. So I think that's maybe why it's not that great of an explanation, and you're right, I think there'd be a better way to talk about it, but there we are.
So the whole idea is that because of the double bond, the bond between 1 and 3 are kind of close. So any substituent that is coming upon 3 might interact with 1. Is that the whole idea?
Yes, I mean it has to do. You're absolutely right. Double bonds are shorter than single bonds. Also, rotation around double bonds is restricted, right?
Okay.
You can't rotate without breaking the pi bond. So this carbon is forced to be sp2 hybridized, as is this carbon, and so that makes it so that whatever's here and whatever's here have to be close to each other.
Okay. So the position of the double bond doesn't necessarily have to be between 1 and 2. It could be between 2 and 3. Because
I think so. What matters is that you have an allyl system.
okay.
Yeah. And this doesn't look necessarily like an allyl system, but because that nitrogen would be conjugated to this bond, that's sort of where it is. I suppose, I'm not even sure I'm getting this right, but you could think of it here, 1, 2, 3, this hydrogen bumping into that substituent. Either way, it's A13 strain. There's no convention for which should be 1 and which should be 3. So if you're interested, go and look at that. Professor Castle has shown that if you incorporate this amino acid at a specific position in a peptide, the restricted freedom about these 2 bonds biases that peptide to form what's called a beta turn, in which elongating chain turns back on itself. He's also shown that if you incorporate these amino acids into peptides, the restricted freedom about these 2 bonds actually makes it harder for proteases to chew up those peptides, and he's interested in applying that to drug development. Okay. Other questions about that? Yeah.
Sorry, just to go back for a second, but with the pentane, when you
Yeah.
like make it a ring, what were the kind of strains it had? Angle and what was the other one?
So we'll talk about this, but rings have angle strain. And did I say something
I
else?
thought you said something else, but maybe you didn't.
I probably said ring strain, but I guess those are the same thing. Okay. And actually, that's exactly where we're going. I want to just see whether... Just want to zoom in on this table. Yeah, go ahead, frantically try to copy everything down. Samantha's not laughing at that one. I'm sorry. Okay, so yeah, maybe we'll start without that. I was going to show you a table of ring strains, but the idea, as we talked about with cyclopropane, is that when you make something into a 3-membered ring, the bond angle has to be something different than is preferred for an sp3 hybridized carbon. Now, we've dealt with that with cyclopropane. Nevertheless, you can calculate, being creative with bond dissociation enthalpies, you can calculate the amount of strain that's present in this ring that would not be present in a linear precursor. And if you do that, you get something that's called a strain energy. And for cyclopropane, it's like 27.5 kilocalories per mole. We don't memorize numbers really, so that's not a number that's worth knowing, but the trends are worth knowing and can be useful. There's nothing really that cyclopropane can do to relieve this strain energy. However, the other size rings can. So if you think about cyclobutane, and if you think about if it were completely flat, the bond angles would have to be 90 degrees, right? And that's also distorted from planarity. That's also tighter than you would want it to be. There we go. So what cyclobutane does instead is it adopts a puckered conformation. What do we mean by that? Well, instead of being completely planar with all of the CH bonds eclipsed and all of the carbon-carbon bonds eclipsed, I haven't drawn the hydrogens in the back because it's hard. Guess we'll still do that. Instead, it relaxes a bit, and the carbons on either end sort of pucker downward, and the carbons in the middle pucker upward, and this relieves some of the strain of the ring, and also because the bond angles don't have to be quite 90 degrees, it also relieves some of the torsional strain between the hydrogens because they're no longer eclipsed with each other. Do you see how if this were a completely flat group, all the hydrogens would be eclipsed? And that's bad. We call that torsional strain, or that's what we have been talking about with butane and pentane. So you can relieve that a little bit, and you can relieve some of the angle strain by distorting its conformation. So we can maybe draw cyclobutane and see what Spartan comes up with. I haven't done this actually, so I'm not sure what it's going to tell us. Just try. This doesn't do any calculations, it just accesses a database that has previously performed calculations. Okay. Oh, and it's already adopted the pucker. So do you see how that's not totally flat? And if you look down the carbon-carbon bonds, we're not eclipsed anymore. We're not perfect Gauche, because you can't be in a four-membered ring, but it's better than eclipsed. So yeah, cyclobutane adopts this conformation. It would be flexible. It would be like a little wing flapping up and down, probably with time. But it does this to avoid the planar structure. Yeah, go ahead.
Does it just like naturally do this, adopt this puckering shape?
Yeah.
So
Yeah.
it's never, ever, hardly ever in the 90 degree?
Well, if you could think about the planar structure maybe being a high energy transition state.
Okay.
Another, I guess, resource that I have that maybe we're up, instead of showing you static pictures, no, that's not what I wanted, of molecules, this gives you basically molecular dynamics simulations of what the molecules look like in real time. So here, well, real time meaning really, really slowed down time. One of our seconds here is 120 femtoseconds in the molecule's time. So this would be happening really fast. And we can control the kinetic energy of the molecule, which can sometimes change its shape. You can see that at 50 Kelvin, it's pretty well in that puckered conformation with carbon-hydrogen bonds wiggling a little bit. If we turn up the bath temperature, we may be able to see it start to shift from one pucker to another. It's hard to tell because now it's moving around like crazy. Another thing we can do is turn down the temperature and try to make it switch from one puckered form to another just by grabbing a hydrogen and pulling. And it looks like it's pretty easy to do that. Cyclobutane conformations are not going to be like chair conformations where you have one that's a minimum and then another that's not. Probably this switches back and forth pretty easily. But I like this app because you can get a sense for what those barriers are. Notice if I move one of these, it'll adjust itself a little bit, and then you can see groups start to move a little bit, but then go back to their equilibrating conformation. All right. Strain energy for cyclobutane is almost the same as for cyclopentane, 26.3 kilocalories per mole. relative to a linear precursor. When we get up to a five-membered ring, that starts being more reasonable, and there's tons of four-membered rings in organic chemistry, but there's even more five-membered rings. Again, if you were perfectly flat here, you'd have to have an angle that was somewhat different than the tetrahedral angle, and you would have all of the hydrogens eclipsed. So instead, the five-membered rings pucker in predictable ways, and people talk about their conformations, but they're not as easy to understand as are the chair conformations. So let me show you a couple examples of the puckered conformations for cyclopentane. One of them is called an envelope conformation, and that is where atoms 1, 2, 3, and 4 are basically in close to the same plane, and then atom 5 is out of the plane. Why do they call this an envelope conformation? Because it looks like this is the envelope. It's so dumb. This is the stamp. Somebody's address. Do you guys even know how to send letters? I'm sorry. Back when I was a kid, we used to send letters to each other. Anyway, that's why they call it an envelope conformation. And there's another that they call a half chair. And this looks sort of like this. And they have, you can see there are sort of pseudo-axial and pseudo-equatorial positions for the six-membered ring. In the half chair, instead of being just atom 5 out of plane, atoms 4 and 5 are out of plane, and then here's 1, 2, and 3 in the same plane. And we won't worry about the relative energies of these conformations. If you want to get a sense for what it might look like, we can draw it. There we go. So, and let's see if it's gonna, no. So this would be a half chair conformation. It looks like you have atoms 1, 2, and 3 sort of in the same plane. And then atoms 4 and 5 are above and below that plane. This can be important. Five-membered rings are important in nucleoside chemistry. So in all your nucleic acids, you've got five-membered ring sugars. One of these is an oxygen instead, and sometimes their shapes can be important. There's also a five-membered ring amino acid called proline, and its shapes and conformations can be important too, so you may encounter that. The strain energy for cyclopentane, let me look at that, is a whole lot less than for cyclobutane. The bond angles, you can do the math, I forget what the equation is, but even if this angle, even if this five-membered ring were perfectly flat, I think the internal angle would be something like 108 degrees, so it's not that bad. And overall angle strain for cyclopentane is about 6 kilocalories per mole. And then our friend, the six-membered ring, adopts the familiar chair form that hopefully you're used to drawing now. And in the chair form, all the bond angles can be tetrahedral, 109.5, and so there's 0 ring strain and 0 torsional strain. Yeah, actually, like strain energy 0.1 kcals per mole. So it's almost like the six-membered ring doesn't mind being a ring at all. It's about the same as in terms of strain as what it would be if it were linear. Feel pretty comfortable on chairs. Do we need to say anything about that? Pretty good. They're just for your edification. Here is a model of or an energy surface for the transition between one chair and the other chair. I tell my undergrads that this allows you to have a secret nerd joke by which you can recognize other nerds at social functions and parties. And the question you ask is, what is the opposite of a chair? And the answer is the other chair. Yeah. Yeah, I mean, only chemists laugh at that. Everybody else is like, okay, moving on. So in going from one chair to the other, sometimes undergraduate texts will tell you you go from one chair to a boat and then to the other chair. Actually, that's not true. When going from one chair to another, you take one of the, in this case, let's see, take one of the down carbons and start to move it up a little bit. This is called a half chair because everything else is still sort of a chair except for that carbon. Then and that's a high energy transition state because you can see all of these groups are eclipsed with each other and this bond angle is going to have to be distorted. Then you go to something called a twist boat. In the twist boat, the two sort of hydrogens that are the masts or the prow and the stern of your boat are not pointing directly at each other, they're sideways. And then to go to the other chair, you have to have them slip past each other. And that is the actual boat. That's a transition state. You get into the other twist boat, go through the other half chair, and then go to the chair. And I wonder whether Spartan has that. I haven't looked at it, but let's sort of take a look as we're finishing. And we'll talk more there later. Yeah, that looks like the half chair or something. No? I'm not sure. Or the twist boat. I'll look at that and we'll talk more about it next time. All right. Good luck on your exam. Do your best. Don't panic. Don't panic. Take a deep breath. It'll be okay. And if I write a bad test, I can make adjustments. So just relax.